today is a talk by Jason on his work in quotation in the context of MetaCoq, and he is going to explain. Also, because lots of people usually ask that, you can start by like maybe 30 seconds saying what you do when you're not working on MetaCoq currently. Because I, of course, didn't prepare any introduction for you, so maybe you can do a 30-second introduction of what you do nowadays, and then we switch to the technical stuff.
Sounds good. Yeah, so what I do when what do I do? My latest project has been trying to formally verify neural nets in Coq. And I'm also part of the Coq dev team and have done a bunch of stuff with the CI and Coqbot. If you've seen anyone say Coqbot CI minimize on pull requests, I put a bunch of work into automatically making minimal test cases for when things go wrong in Coq. And I guess generally, I also have an eye towards performance of Coq, performance of proof assistance, performance of automation. And maybe you can tell I'm saying this all off the top of my head. But I think the thing that I tend to do the most is like push on performance of proof assistance and be like, what if we try to do something that's like 10x bigger or 100x bigger than other people have tried before?
Right. And now, actually, I think the talk is going to be about something that's a lot bigger than other people have tried before, because you're working on a nice theorem, but really for the real-time theory of Coq. I think everybody is here, so we can start with your talk. Let's say about 30-ish minutes. Huh?
Asya is not here.
Yes, but Asya is out there and Mathieu is out there. So maybe if you knock once so they know we're starting, and then...
The cigarette isn't finished, so...
Okay, yeah. So I think we can go ahead. They will come in a minute. So about 30 minutes. We are not specifically in a rush. Stage is yours.
Cool. Can you all see the slideshow?
Yes, yeah, we can see your slides.
Okay, great. Okay, so the way I want to run this talk is that I'm going to give a little bit of context on what I did, and then I want to spend the bulk of the time on a sort of code walkthrough driven by what you all want to see. And the context that I started working on, what I've been calling MetaCoq quotation, is Loeb's theorem. And Loeb's theorem is this theorem that says if you can prove that X is true whenever X is provable, then you can prove X. In symbols, you can all see my mouse, right?
Yes.
Okay, so in symbols, it says this box of box X implies box X. Loeb's theorem is hard to fit in your head because there's 3 different levels of quotation that you need to manage at the same time. I put a little bit more prep work into this presentation, I would have color-coded it, but there's this arrow outside of any boxes. There's things that are under one box, which is this X and this arrow. And then there's this X, which is under 2 boxes. And you need to keep these all separate at the same time. And juggling 2 levels of quotation is hard. Juggling 3 levels of quotation is even harder. And I think that's what makes Loeb's theorem sort of traditionally hard to understand. And here, box X, I'm playing a little bit fast and loose with when I use quotes and when I don't use quotes, but box X is roughly you have an AST for, you have an AST and you have a proof that the AST has the type that you're claiming here. And roughly when I've tried to make it so that when I use quotes here, that corresponds to this quotation operator in MetaCoq. This is all valid MetaCoq syntax on this side. And the most challenging building blocks in proving Loeb's theorem in something like a real proof assistant are that you need decidable equality of ASTs, and you need this quotation operator that goes from box A to box A, that adds an extra layer of quotation. And I spent some time doing decidable equality of ASTs. We mostly have that in MetaCoq. There's some issues where it relies on axioms still, where like, I think there's some functions in the handling of universes in ASTs or something. And so you end up using functional extensionality, which is not the best, but with those axioms, we have decidable equality of ASTs. And the real question is, how do we get quotation? And everything else in doing Loeb's theorem is comparatively straightforward. to getting these two building blocks, and I have an Ogdo formalization of most of it. There's a possible exception, which is that you, in order to prove that, so Loeb's theorem is a fixed point operator. In order to prove that the thing you get is actually a fixed point, you need some equational reasoning about how reduction acts, and I haven't looked into how hard it's going to be to prove reduction about the things we're quoting. That might be even more tricky. And the thing I'm going to focus on here is the quotation, which I think is by far the most challenging building block engineering-wise, even though it's conceptually relatively simple. And so in MetaCoq, I said already, this is how we define box. And quotation, if you like category theory, you can say that it's cojoin of the lax monoidal semicomonad box. If you don't know what that means, that's totally fine. It's just that it's this type signature. And the way that we want to define it is that it's a pair, basically, where, because this is a sigma type, we need to say, what is the term? The term is going to be itself a pair of quoting the term and quoting the typing derivation. And then you need to prove that each of these things are well typed. And the type signatures for all of these, we have quote term that sort of adds a layer of boxes on terms, quote typing that turns a typing derivation into a term. And then there's two more parts which I have not yet managed to formalize yet, which is proving that quote term is well typed and proving that quote typing is well typed. And these are the type signatures that you would want for these two pieces. And I'll leave these up for a minute so you can see them. I can also post a video of this later if any of you want to look at it, or also post a link to the slides.
So why isn't your quote term well typed? You start out with a term that has type T and gamma, but then when you say quote term T, it's actually closed.
Right. So the thing that we want to do is when we quote, so if you look at what quote typing does, the thing that quote typing is supposed to do is it says you have a term that has a type in some context, but when you add a layer of syntax to this, there should be, this typing derivation shouldn't rely on any like Galena context variables. And so when you add a layer of syntax, you'll get a syntax for this typing derivation that proves something about T in the context of gamma, but that syntax itself should have nothing in its context. So here, the quotation of the typing derivation has nothing in its context, but the typing derivation itself has a non-empty context. Does that make sense?
I was actually talking about the quote underscore term underscore well typed line.
Yes. Right. So the thing we want to say again here is that even though T, let's see, did I mess this up?
No, it's all good, I think.
No, I think this is let's see. Right, so here we're not quoting the typing derivation. We're saying that, wait, maybe, you know, I think this premise is unnecessary. I think maybe the way that quote term well type is supposed to go is it just says that quote term T always has type in that term, regardless of whether the thing that you're typing has a type or not.
Okay.
Yeah, I think this premise should not be here.
Okay.
Good catch. Okay, so that's the context broadly. The rest of the talk is going to be code walkthrough. Stats on the code, there's about 8,000 lines of code, took about 200 hours to do all of this. This is only the quote term and quote typing parts, which has me a little bit worried about how much work it'll take to do the well-typed parts, given that the usual standard is that proof adds an extra 10x to 100x overhead. So what'll that be? 80,000 to 800,000 lines of code and 2,000 to 20,000 hours. And I have some stuff to say about what the most challenging bits there are. But okay, so what actually is in all of this? The broad overview of the code walkthrough.
Can you make
that I've done this.
a bit bigger font size wise? The font is a bit small for us.
Is this bigger enough, or do you want bigger?
Let's ask the people.
Bigger,
please.
How's this?
People exit.
More big?
Big.
Make this. Is this good or more big?
More
Bigger.
Okay.
Like this?
Yeah. It's good.
Okay, great. Okay, so I did this all both for the template AST and the PCUIC AST. The code for these is extremely similar and it's largely automated. And roughly the high level, the like interface that users are going to see, basically anyone who wants to use this is probably just going to want to invoke one of these definitions. And here we see the quote term and quote typing. And I also did this for reduction and WF local, WF, WFX, and WFAST. And I'm not sure how useful these will be. Probably at least the reduction we'll need for proving equational laws. And I haven't quite figured out how much we'll need the WF things, but I basically took the approach of let me quote almost everything in the dependency chain and write some automation to do this. And the way that this is all set up is that, okay, so I have some design principles. I'm just going to like go through this. I built this largely around type classes to manage the automation for constructing the functions that go from T to AST.term. And roughly the reason to do this is so that I can build the building blocks sort of automatically, where if you need to quote your ASTs, you want to also be able to quote all the types that are used in AST. For example, if there are Booleans in some places, you need to be like, what does it mean to get syntax for any Boolean? Well, it means that if the Boolean is true, give me syntax for true. Maybe I should, yeah, okay, so can you see my terminal?
No.
No, okay. So let me see if I can switch that. Okay.
Yes. No, we can see.
And could you make it bigger, the font size?
Yes, thank you. Better? Bigger still?
Yeah, still bigger. Yeah.
Terminal is being slow to load. I did not adequately prep this. Sorry for the delays. Is not usually this slow. Here we go. Okay, so nope, wrong version of Coq. Version. byte is is relatively slow. Okay, so you're like, how do you quote a Boolean? And the way you quote a Boolean is you're like, if the Boolean is true, then you're the constructor 0. If the Boolean is false, here, I'll just make this full screen. If the Boolean is false, then you're constructor 1. You're like, if the Boolean is true, then we'll just give syntax for true. If the Boolean is false, we just give syntax for false. And basically the thing that we need to do to get the quotation working is to build up this tower of quoting syntax, starting from the very basic types in Coq all the way up to ASTs. And so going back to the design principles, I built this around type classes. The universes is one of the things that's like most painful to deal with. It's also the biggest open question in how to deal with typing. I think that in making typing work, the future work for how to get well typedness of these, the biggest roadblock right now is how to deal with universes. The second biggest roadblock is getting the safe checker to produce unsquashed typing derivations, but there's some indication on Zulip that Theo might be working on this. And the way that I handled universes in quotation is that I sort of systematically refresh them. This is in part because TM axiom and TM definition don't support emitting universe polymorphic constants. What other things do I want to say here? There's this trick for quoting things in prop, because normally you can't say like which prop do I have. But if you can decide whether or not the prop is true, then you can quote the decision procedure and basically say, if you know that the decision procedure returns the left side, you can take a proof of egreffel, or you can take a proof of equality, which you can always quote as egreffel, and in the empty context, and then you can reconstruct the proposition, and you use that for quoting propositions. The directory structure roughly mirrors the underlying structure of MetaCoq. What else do I want to say here? Yeah, so the way that I set up the basics, so there's some common utilities that I define that does some like manipulation of kernel names, adjustment of universes, getting the body of opaque constants, because we need to be able to quote even opaque things. And then the main type classes that I built for this are this quotation of, that's like, if you have a particular term, here's the syntax for that term, and then saying that a type is quotable in the empty context, which says that for everything of that type, you can get the quotation of that element. And then there's some classes for managing automation around inductive types, for managing automation around Boolean context variables. All of this is in the README. Yeah, there's a bunch of module type structure. So if you're interested in like really digging into the code, there's all of that. And I think at this point, looking at time, okay, so the other anticipated major work in future directions are that we want to deduplicate the work that the safe checker does by abstracting over Galena context variables. And I think you can do this by just moving the abstraction into the term level. but I haven't validated that this approach works. If we manage to solve all of these and get typing for quotation, there's the question for Loeb's theorem, we need to use the same axioms in the meta theory and the object theory. Ideally, this would be the empty set of axioms, but right now the meta theory is using like function extensionality and some other things for doing, for example, decidable equality of ASTs, and also all the axioms about the guard checker. And then I'm also concerned, finally, about performance and scaling, because we'll have to take this whole well-typed quotation thing and quote it and prove that it's well-typed. And so this entire development, the 8,000 lines of code plus whatever it takes for typing, the safe checker will also have to be able to handle checking something of this size. And so that's what I see as the like somewhat daunting bits in future work. Okay. I'm happy to now spend however much time people want going through various bits of code and answering questions. Thank you all for listening.
Go ahead.
That's some very cool things. I have a question for kind of the broader picture, because I'm not very like familiar with the whole Loeb theorem setting.
Mhm.
And I know that like one of the big applications is to show some form of incompleteness theorem.
Yep.
Like if you manage to prove Loeb theorem, how far are you from like a formalized Gödel incompleteness for MetaCoq in Coq or something like this?
One line of code, instantiate
Okay.
X with false, and you're done. Right?
Okay,
If you
great.
instantiate X with false, you
Oh,
say,
yes.
if you can prove that there is no proof of false, then you
Yeah.
have a proof of false.
Okay, excellent. Oh, that's really cool, because I think it's something that's been around for like since the beginning of Coq. That's bummed everybody that like you can't really prove Gödel's incompleteness for it. So that would be a very nice thing to have.
Yeah.
I think independently of Loeb, the quotation theorem you are doing, you also need for direct proofs of incompleteness. Like it's
right.
not that
Yes.
connected. It's also connected to Loeb, but it's also
Yeah.
in any incompleteness proof,
Yeah.
you start with for sure probability of probability is equivalent to probability.
Yeah.
Number
Are-
one, and then
Are there any incompleteness theorems or like any proofs of Gödel that don't route through some sort of take the fixed point?
second
Like-
incompleteness theorem, no. I think for the first one you don't need that. For sure not. No, for the first one you don't
Yeah,
need
because
that.
you have cardinality arguments of some sort.
Or like these computability arguments.
Yeah.
But for the second one, no, it's in the end, it's always, I think, a similar proof.
Wait, what? Remind me what the first one is again?
There exists like this, the system is not no system such that whatever preconditions is complete in the sense that you cannot prove for every formula either the formula or its non-provability or its negation. And then the second one says
Yes.
actually it singles out a sentence which is incomplete, namely consistency.
First one says there is an independent sentence, and second one says consistency is independent.
But if you do a constructive proof of the first one, doesn't the proof need to exhibit the witness?
Yeah. So constructively, you don't prove that; you prove something else.
Yeah.
But still, the second one in particular proves that consistency, like the statement of consistency, is this independent sentence.
Right. Yeah. And like Loeb's theorem is also more general. And like if you strip out the boxes, you get the Y Combinator, which is more or less also how you prove the like any sort of diagonalization argument or that the halting problem is undecidable also routes through this sort of thing. I can't tell if my audio is coming through because the
No.
computer is
All good.
laggy. Cool.
I didn't understand the deal with propositions. Why do you need to write deciders for things in prop?
Because you can't do propositional. If I have A or B, and I want to build a syntax tree out of this. And I'm like, well, I know how to quote proofs of A and I know how to quote proofs of B. The first thing I need to do is I need to say, well, did I have an A or did I have a B? I'm like, oops, when you have a prop in Coq and you're trying to build an AST, which is in type, you can't actually eliminate the disjunction and see which side you had.
Yeah.
More questions for Jason?
What's the current status you have? What theorems?
The current status is that we have the ones in black are done, modulo the axioms for decidable equality and the guard checker and all that stuff. And you can see this in the main branch of MetaCoq. I think it was just recently merged into main in these all files. So these ones are they're all proven. There's no admits remaining. The well-typed theorems are very much a work in progress. I have a branch where I've started playing around with it, but you hit universes basically in trying to prove that that like any container data type is well typed. You're like, I want to prove that quoting option is well typed, or I want to prove that like quoting Cartesian product is well typed. And there's already the question there of how do you manage universes? And I haven't figured out a good way yet of doing this like automatic management of universe polymorphism or of universes. But I have this branch where I'm sort of starting to play with that stuff. But this is not really under active development. It's been at least like 6 months or a year or something since I mean 2 weeks ago, because I was making sure that it builds for this, but before that, this was all rebasing. So I'm not actually going to get a good state. But yeah, I have this branch where I'm starting to play with the typing. And so the typing is basically not done at all. Whereas the building the terms is basically finished.
So can you also do box A to A in your setting? Because ultimately, if I want to have quoted something, I do want to, run it maybe eventually. And
yeah, so if you can do box, so basically Loeb's theorem says that if you can do box A to A in a way that is quotable, like if you have a Galena function that goes box A to A, then your system is inconsistent.
So, but then what's the? That's right.
So
but in some sense, I do want box A to A.
Right. So I think the thing that you want, the idea that I had for this is that you want to sort of parameterize box A to A, where you want to say, if you hand me a denotation function for the inductives that you care about that handles enough universes, like handles all the universes that are going to show up in your term, then you can build a denotation function. And you might even be able to get away with translating all the inductives to W types. I'm not sure about that, although it would be nicer if you like give me the denotation function for the inductives and then I'll like directly denote them. I have thought about how to do this. I haven't explored it that much. I think that there's a thread on Zulip where I was asking some questions about like, how feasible is this? How do we do this? I think it's a very interesting area and would love to see something around this. And if I had more time, I would be working on that as well.
What about box A to box A? So
yeah, I think
because of the quotation theorem.
That's going to have the same problem because
Box
you can.
Right.
No,
I think that lets you prove inconsistent if you wrap another layer of boxes around everything.
Of boxes, and then you get rid of the boxes in the box.
Like I think that might give you box false or something.
Are you sure you can't get bottom box bottom? Like
I think you get box. Yeah, okay. I think what happens there? So if you have box A to box A, then consider A equals false or X equals box false. Right. So then you have box false implies box false, and you quote that, and so you get box false.
I can't do the unboxing in my head anymore because you're our
Okay.
ninth talk today. So
Let me here, if we make a new. My computer is being a little bit laggy, but does this make sense?
And assuming you will have that, yeah, okay. Then you could have box false, which is problematic.
Yeah, I think really the way that
What's the scope of that X? I mean, like, how can you
Sorry.
put X inside? How can you put X inside the box and the outside the box, like, at the same time?
yeah. So what is this at? You're like, what is the type of X such that this works?
Yeah. What is the scope
so-
of the X?
Yeah, so I think we want X colon AST, or actually we want okay, the thing that we actually want here is X colon box type. And
I mean, then first is not the box type, right?
there is some hidden quotation going on in here where I think when the more, how to say this, there is a way of rendering this such that this just works. But
I mean,
How does this-
I think there is an X that works that kind of that there is an X that allows you to define the loss theorem, but I'm not sure whether that kind of X also allows you to encode, for example, first there.
For sure.
also allows you to encode what?
Encode first there, like put
False.
first there. Yeah, like that.
I mean, the way that you encode false is basically you quote false. I mean, okay, so technically, I guess we want to say this. Right, where quotes here mean that I've quoted the inductive type false and I've given a proof that it has type. Or I think the way that we set this up even with boxes defined like this, right? You can just literally stick false in over here. And then the goal is to be able to prove Loeb's theorem like this, where in the statement of Loeb's theorem, you don't have this like meta language quotation here. Instead, you're just taking in a term that gets slotted into the type slot. And if this seems a little bit wishy-washy, that's because I've haven't encoded this part of it, of the construction yet. Though I think in theory, I do have a formalization of a decent chunk of this in Ogda. So in theory, if I had the time to spend, I don't know, 2 to 4 weeks, I could probably get the formalization of Loeb's theorem where I sort of axiomatize the well-typed bits, and then just rely on those axioms and get the rest of it in Coq.
I think we're actually reasonably well in schedule if we now call it today. Thank you, Jason, for taking the time
Thank you.
to talk to us. Yeah, we'd be definitely interested in the recording. Let's thank Jason again.
Yeah, thanks everyone. And I'm happy to answer more questions or chat more about this whenever.
I think we'll be interested in that. As I said, like we had a long day today with 9 talks. So I think now the schedule insists that we go have beers.